All right, good morning and welcome to lecture 26 of Quantum Physics for Non-Physicists. Today's the 10th of December, and today we will put a break on thermodynamics and talk about something very basic in quantum mechanics, which is the uncertainty principle, which I'm sure you've heard a lot about it. And so this is following chapter 4.5 of the book of Schumacher and Westmoreland. And our daily analogy for today is kind of a cheat. It's not really an analogy, it's the actual thing. What you see here in this picture is a picture from a bubble chamber. And what this is like a big chamber where there's some kind of liquid, which is usually something like liquid hydrogen, so H2, but in liquid form. And what happens is that when a charged particle kind of enters this chamber and moves about, it will touch the particles in this liquid. So liquid is like a gas, but more dense than a gas. Okay, so this particle is coming, it hits the particles that are in the liquid, and these particles in the liquid will do something. So depending on what exactly the material is here, they will either kind of, from the energy they get from the from this particle, they can either like evaporate a little bit and form kind of bubbles in the path of the particle, much like, and here's the analogy, much like a plane in the sky will leave this like this trail. Or maybe they ionize and then there's some way to detect this ionization. So what you see here is kind of a photograph of this chamber from above after such a particle has passed through. So what we see here, much like the jet trail, so much like the jet trail, there we go. I'll replace it with a proper drawing, is we see the path of the particle, right? And to see the path of the particle means that, well, from the path here, we can reconstruct what the position of the particle was and what the momentum of the particle was, right? Because if we didn't have the momentum, meaning the velocity of the particle, it's a mass, then we would not be able to see the position later, right? So if we know the position here and then a bit later, then we know the momentum. And we know the position. And this is a bit strange. So by the way, from here, people can calculate lots of properties about particles, and a lot of like particle physics and discovery of new particles comes from the analysis of this kind of chambers. Because from the orbits, you can see, for example, what the charge of the particle should be, and so on, by applying different fields, etc. But the surprising thing is that from it looks like from the outside, it's like we're doing a measurement at every point, right? Which tells us both the position and the momentum of the particle. But, however, if we took quantum mechanics seriously and we did a proper position measurement, right, a perfect position measurement, then what is the state of the particle after this position measurement? Then it would be exactly, if we get outcome x0, then the particle collapses to x0 perfectly, right? And what is x0 in particular, if we transform it to the p basis, right, then you get this Fourier transform, which means that it's a superposition over all the momenta. Which means that this particle is like perfectly well localized, but the momentum is completely out of undefined, which means that if we wait a little bit of time, then in the next moment it could be anywhere, right? But this is not what we observe here. Here we observe that we see the position of, obviously not to infinite precision, but to very good precision, but we also see the momentum to very, very good precision. And the uncertainty relations are a way to quantify this. Probably the way that you've seen the most is in this form, where we have that the uncertainty over the position and the uncertainty over the momentum are larger than h bar. And remember that h bar is a very, very small number. So it tells us, usually people look at it as a fundamental limitation, like it tells us that we cannot know both position and momentum to absolute precision at the same time. But I like to see it more as a proof that we can get pretty close to absolute precision, right? This number is really, really small. And this is the reason why we can observe these trajectories. Okay. In terms of housekeeping, as I said in the email, I still owe you 40 minutes of lecture, more or less. So I will upload another lecture with this, where we'll finish the thermodynamics part. News about the exam, it's been booked now. I think you got an email, so don't quote me on this, but I think it's 19th of February. And I will publish a mock exam in early January. So something that will have the same structure and the same kind of questions as the exam. And then we'll have question sessions in both January and February. Okay. Good. So let's just see where we are. We did last time, we did Lindblad evolution. And today, the only thing left here in the certainty is uncertainty relations and entropy. I don't know how much I'll be able to talk about entropy. Definitely in the tutorial, there'll be an exercise about this, but we'll see. And then the only thing missing in the big picture that we'll spend next week doing is 3D problems. Yeah. Where we can see a particle trapped in a 3D potential and see what happens there. Okay. So then let's get started. And we need to do a little bit of recap from something we've done many, many lectures ago. Okay. And this was up. We saw that we defined some observable A as the sum over this lump. No, let me do this. We define an observable A as a sum over the different outcomes and a label for the outcomes and the projector of the outcome, right? And this thing had the property that it was Hermitian, because these are real numbers. And we saw that the average of a quantity of an observable for state rho, this is just trace of a rho, which in the case of pure states this became just that, right? And the variance was defined like this. Sorry, let me just see if I'm getting this in the right order, which I usually don't. Yeah. Yeah, that's right, yes. Okay, so this term here, A square is just sum over K lambda K pi K, sum over L lambda L pi L. And if we assume, if it's a projective measurement, so this means that if there's no overlap between these different projectors, so you get KL pi K and they're projectors, so they're idempotent, then we get that A square is the sum over K lambda K square pi K, right? So then trace of A square rho because the trace is linear, it's just K squared trace of pi K rho. That's this side, and then on the other side we have the trace of this times 2. So let me just write here. So this is sum over k, lambda k, trace of pi k rho. Very nice. We missed some hats. Okay. So here we get this times itself. So sum over L, lambda L, trace of pi L rho. That's an L and that's a rho. So that's sum over KL, lambda K, lambda L, and then trace of pi K rho, trace of pi L rho. Okay. And what's important here is to note that each of this is smaller than 1, unless they're perfectly aligned. In general, it will be smaller than 1, at most 1. So when you multiply two things that are smaller than 1, the result will be smaller than the original. And that's why, I mean, in general, this number here is going to be smaller than this number there. Okay. I left a k behind. That belongs here. Okay, so this is things that we know from a long time ago. And now we want to show the uncertainty principle. So we're going to define the variance in a slightly different way first. So continued, and let's just define it like this. Delta A as being the variable itself minus the average of the variable for the state times the identity. To see that this gives us the same definition as before, we can do, well, what's the trace? Oh, sorry, what's delta A squared evaluated to? What's the average of this value? So this is trace of delta A squared rho. And what's that? Well, that's trace of A squared minus 2, this average, that's a number, and then A. I mean, you can have the identity here, but that's nothing, right? Plus a rho. Took. Sorry, there's a square missing there. Okay. And now we can just use the linearity of the trace. So this is trace of what? A squared rho minus 2 times this number. And now trace of A rho plus this number, trace of rho, right? So that's this. This comes from there, that comes from there. Okay, so now let's rephrase things. So this is just the average value of A squared, right? Just like defined before, just like here, right? That's this. Okay. this thing here, well, that's just a definition of a row. And this trace of row, because it's a density matrix, it's normalized, so the trace is 1. So then we have -2, and sorry, this row should be on the outside, a row squared plus a row squared. Okay, so these two terms are the same, so we get a square of row minus a row square. Okay, which is exactly what we had before when we define this. Okay? Which makes sense because the variance is supposed to measure how much our distribution deviates from like a perfectly peaked distribution around the average, which would be this thing here. Okay, good. So now we have this definition, and now we're going to do something with it. The goal is the following. So we have two observables, A and B, and we want to bound delta A, delta B. Okay. And this will turn out to be larger than one half of the absolute value of the commutator of the two for our state row. Okay, very good. So this is what we want to prove, but we might not want to, I mean, we didn't have to start like knowing what the result will be. We could just try to find a way to bind these two things. And we'll do it here for pure states, because for mixed states, it can only get worse. And if we have time later on, then we'll look at what happens when we have well, to write it not in terms of the answer of this variance, but in terms of the entropy of the probability distributions after each measurement, and then we get a much nicer relation, which can be generalized for cases where we have, for example, a quantum memory. This kind of things is a lot of fun. Good. All right, so let's get started. And first, we're going to define, we need a bunch of ingredients first, okay? So first ingredient is that the commutator of the variance is the same as the commutator of the original density matrices. Okay, and to prove this, well, we can just compute it directly, right? So if delta A, delta B, what is this? This is delta A, delta B minus delta B, delta A, but let's take the definition of this variance. And note that this definition is kind of with respect to a specific state already. So we get A minus A identity, B minus B identity minus the opposite Okay. Okay, so let's just do all the terms. So we have AB minus AB minus AB minus AB identity, and now minus BA minus, plus BA plus BA minus BA identity. Another nice thing is that most of these terms cancel out because look, this term is the same as this because what's in between brackets is a number, right? So obviously it commutes. Chuk, this is the same as that. Oh, and this should have been a plus here. Up. Should be a plus there. There you go. Okay. So then we get AB minus BA, which is the result that we wanted. Good. The second ingredient that we want is this inequality that says that is called the Schwarz inequality, which says this, that for two vectors which are not necessarily normalized, then we have that the product of the product of their inner products is larger than AB squared. Yeah. This is kind of a dry derivation because I'm really giving you all the ingredients, but this one we will not prove in the lecture. So I'll put this in the tutorial as an exercise. Otherwise, it would be here all day. The other ingredient that we need is if we have two operators, then this is just the sum over plus 1, 2 of the commutator plus the anti-commutator. Okay. And this is kind of direct because what we have here is just 1 over 2 FG minus 1 over 2 GF plus 1 over 2 FG plus 1 over 2 GF, right? And these two cancel out, so we get the same thing there. And we need one more ingredient. Let's just number our ingredients. Ingredient 1, 2, 3, and 4. And that's if F and G are Hermitian. And by this I mean that F equals F dagger, G equals G dagger, then 1. The commutator is anti-Hermitian. 2, the anti-commutator is Hermitian. And 3, whenever I do the expectation value of the anti-commutator, this is always a pure imaginary number. Okay, so we're going to just show all these things. And they are rather straightforward to show. And these are all ingredients that we need for later. So if you want to do, first let's write what the anti-commutator is, fg minus gf. And now if we want to do the complex conjugate, so the complex conjugate of a product of matrices is given, you need to change the order of the matrices and take the complex conjugate of each of them. Right, so if you do this here, then you get gf minus fg, but because each of these matrices is Hermitian, then you can just replace the gf minus fg, and that's minus the commutator, right? Good, and the same happens here, so fg minus gf, sorry. This is the commutator. If we take the complex conjugate, then we get gf plus f dagger g dagger, and that's just gf plus fg, which is okay. Good, and now here, to show that this is a pure imaginary number, well, let's just call K to be this commutator. It's just a matrix, right? And then, so if we take K dagger, and we want to take this, then we know that this is the same. So sorry, the complex conjugate of this, we know that, sorry, give me just a second. Where do I have this? Yeah, that this is the same as putting check the complex conjugate here, check, right? But we know that this is this is Hunter-Hermitian, so this is going to be minus that, right? So then you get minus I, k, I, okay. So what's the number? What kind of number? So think of this number as some alpha plus beta I, and this number, so sorry, the complex conjugate of the number would have to be alpha minus beta I, okay. And if this is minus this, then the only option is that this is this alpha is 0 and the number is a pure imaginary number. Okay, good. So then all of these facts together, it kind of tells us that we can always write fg as the imaginary number times some matrix, where this matrix is Hermitian. Okay, so K equals K dagger. So I'll just put another, let's call this K bar, so we don't confuse them. Okay, good. So if you have two observables, and observables are always Hermitian, then the commutator of them is always an observable times some I. For example, we know that X and P is I H bar identity, right? So this is our K. We also know that, for example, if you take the poly X and poly Z matrices, then this gives you I poly Z matrix, okay, which is an observable again. All right. Good. So these are the examples that we needed. And with this, we're kind of ready to start. Okay, now it's with this proof. Okay, so we just defined these two vectors. So I'll follow the book derivation kind of closely. It's not necessarily the nicest derivation that there is, and to prove it for pure states only. So we define A as being this observable that we have before applied to a state psi, which will be the state of our system. Okay, and we do the same for B. Delta B applied to the state of our system. Okay. Now, note that delta A and delta B are also emission. Now, if we want to know, well, what do we want to know? We want to know this delta A squared delta B squared, right? Well, what is this? This is just our state, and now comes the delta A squared state, and here comes state delta B squared state. Okay, and now because this delta A is a Hermitian thing, I can write it as delta A Hermitian delta A psi, and here the same subtook delta B dagger delta B state. Okay, so this is just A B B. Okay, and now we use this ingredient that we had from before. Up, where is it? We'll use this ingredient here. Okay. So say that this is larger than AB squared. So this is larger than AB squared, which is what? So it's psi delta A, which is the same as delta A squared, delta B check square, right? Okay, so far so good. Now, what we'll do is we're going to take this and replace it with a commutator by using the commutator and the anti-commutator of these two variables by using this third ingredient here. Okay. So there we go. Psi delta A delta B psi. Well, this is the same as everything. Psi 1/2 of the commutator between delta A and delta B plus 1/2 of the anti-commutator between delta A and delta B. Okay. Good. And now we can replace already, well, let's just put it 1/2 of psi. We can replace this already with K. Okay. Plus 1/2 took, and now this anti-commutator. Where here, remember that k is just, or ik is the commutator of A and B, and we use this first ingredient. We use this first ingredient that the commutators are the same for the variance and for the original observable. And we know that K must be a Hermitian matrix. Okay, good. And we are almost done. So, and now let's look at this as taking this I beta plus alpha, okay, where alpha is this and beta is all of this without the I, okay? Good. Or we can even put, one half of, sorry, let's put like this, 1/2 of I beta plus A, because this will make our life easier. This is A, this is A, that's B. Okay, so we're trying to bound this thing here, right? So what is check delta A, delta B, check square? Well, that's going to be 1/4 of alpha squared plus beta squared, okay? Which in particular is larger than 1/4 beta squared. Okay, so this is a very loose bound for now. Right, so I just took this, I computed the absolute value, so that's this plus that. Oh, sorry, that's a lie. There you go. This is still true though. So I computed the absolute value, and then we just bound it by saying, well, let's get rid of this A for now. Okay. Because the alpha is not doing anything. Okay, so then we have this. Let's put everything together. So what we had on the left-hand side was this thing here. Okay. And now on the right-hand side, we have 1/4 of beta square. So 1/4, and what is this beta now? Well, beta square is just the absolute value of this thing. Tac. K. Tac. Right, and we can even replace what the K was. Because it's inside the absolute value, it doesn't change anything. Check, there you go. Right. Okay. Good. So this is kind of the kind of raw form of the uncertainty relation. And then if you want, then you can work out this these squares there and simplify it to delta A, delta B being larger than 1/4. And then check AB, check. Okay, without the squares. Well, I don't think we'll do this in a tutorial, maybe in a further exercise. Okay, so what are some examples like we saw before of this? Again, if you have x and p, we know that this is IH times the identity. So then we know that the product of the variances is always going to, oh, sorry, I forgot that this should be a 2 here, because we got rid of the square. Then we know that the product of the variances is always going to be larger than h bar over 2. Yeah. Oh, yes. Sorry, I forgot a sign of a half a long time ago. Yeah, this is correct. And here is missing. Good. Okay, another example is in a qubit. If we define the observables for spin, for example, x is being h bar times the Pauli matrix, which we've seen a few times, and so on, then we know that, for example, delta uncertainty in the spin, it's always going to be larger than h bar over 2 the other direction. Okay, and this is going to be the value for our state. Everything is defined with respect to the state of the system. Okay, this because we have this commutation relation where here it should be the z. Yep. Okay, so we will see maybe an example or two in the tutorial next week. And you know, this is important because it tells us how compatible the two observables are. Okay? So for example, this is why you can measure the state of 2 qubits or of 2 particles perfectly well. You can measure the position of one particle and the position of the second particle perfectly well, because these two observables commute because they act on different Hilbert spaces. The same if you want to measure this z spin direction of one qubit and the x direction of another qubit. These two observables commute, so then this term here is 0, so which means that in principle you can measure them simultaneously. However, if you want to measure 2 directions of spin at the same time, you're never going to be able to do this, because the moment you measure one, you're disturbing the state. So if you want to measure the second one, then the result will have very little to do with the initial state. And the second, I mean, the easier way to see it is that if this commutator is non-zero, then they don't share a basis of eigenvectors, right? And as we saw, for example, in the example of the wave packets, the more particle is localized in position. So we have this short Gaussian for position, then the Gaussian, if you write it in momentum basis, we saw that it was very wide, right? And vice versa. So if something is very well localized in position, then it's very spread in momentum, and so on. Okay, and all of these relations are captured by this, by the uncertainty principle. I don't like it too much because, again, it depends on how we label the eigenvalues of our observables. So for this, it's much better to think of the kind of entropic uncertainty relations, which I'm sure it's talked about in the quantum information theory course. I don't know if we will have time to go into it in this course, probably not. But that's it. Okay, so thank you, and I will see you next week then. Ciao.